So I'd like to thank the organizers for allowing me to present. It's a pretty broad audience, so I'm going to try to present a pretty broad topic rather than diving into details. And I'm going to motivate the work we're doing in our group by the question, is Moore's law going to continue forever? So this is a chart taken from 2005, updated 2009 from the free lunch is over. What people plot is the number of transistors that are sitting on a chip, and it's still growing exponentially. But you all know that the clock speed has basically tapered out at 2 gigahertz about 10 years ago, 12 years ago. And that has to do a lot with the power consumption that is on these chips, which has about tapered out at 100 watt on a single chip. And also the performance overall has been limited of what these computers can put out. So let's look at a little bit about where this power limitation comes from, and let's try to understand it and put it in perspective. So 100 watt per square centimeter is roughly the power density that you have a nuclear reactor. I don't think you want to go a whole lot hotter than that, and you can't. So basically this is a chart taken from 2004 from an Intel forum, and it's of course tongue-in-cheek saying that we can't go hotter than what we have. So the question is, where is this power getting lost? Where's the heat being generated? And in today's technology, we basically have a latch switch, 2 transistors that basically hold a 1 and a 0. And basically, the beauty of a CMOS transistor is that it only consumes power supposedly when it switches. And you can write down the power that's being consumed. It's the frequency of switching, the bucket of charge that you empty out and fill up, and the voltage that the capacitor is charged with in the square. So that's the dynamic power. So you can run your computer slower. You may not want to do that. You can work really hard to reduce the device sizes and make capacitances smaller. That's a lot of work and it's very expensive. Or you can reduce the voltage. And that is what has been done for about 30 years. But now voltage has scaled to about 0.8 volt, and that is it. And one of the reasons is that the static power that is actually flowing through this transistor set here has a certain power dependence as well, or voltage dependence, and that happens to be inversely proportional to the exponent of the voltage that you operate this thing in. And I'll show you some examples why that is and how that is, to give you physical insight. So when you hear people about Moore's law continuing, you can argue with them that that is not going to happen. So here's a traditional switch. You have a source and a drain, and you have a gate, which is basically a barrier for electrons that are flowing. But there will always be electrons flowing. However large you will make this barrier, you ultimately will have electrons flowing within the thermal tail. And as you lower the barrier, you expose more electrons that can flow, and there's a certain slope. That slope is 60 millivolt per decade, meaning 60 millivolt change in here will give you 1 decade, a factor of 10 more current. And that is a fundamental layout of this switch. You cannot change it, and eventually the switch saturates, and here's your basically simple transistor that is going on and off under a voltage. You cannot change this slope fundamentally in this switch layout. In fact, most transistors will have a slope that is not as steep but shallower. And an ideal switch, in a way, what you want is you want to go from 0 to on in the least amount of work that you can do. So you can have some expressions for this, why the 60 millivolt per decade. You can even do it analytically. Let's leave it like that. The problem is that this is a fundamental limit of this switch. So what has happened over the years? What has happened is that people built a quote-unquote ideal switch that turns on in this shape or form, and then they say we're going to lower the voltage. Okay, so they lower the voltage, and what happens is really that the leakage current here for no voltage applied, or for supposedly the offset, goes up exponentially. And that is being seen even in experiments. So as devices have gotten smaller and smaller, basically the leakage current is creeping up to the dynamic power. So today's transistors burn as much power when they're not operated as well as when they're operated. So that's a pretty big problem, meaning you generate a lot of heat whether you're working this thing or not. Now, there's a whole slew of people that are interested in overcoming this fundamental limit. And one way of doing that is to say, what we really want is, we want to bend this spaghetti over, right? We want to make this steeper and have a better switch. So, one way of doing that is the following: to get rid of the thermal tail of the electrons that are really dominating this slope. If you can put a barrier here and cut off that tail, and you can have a barrier in between that turns on and off this transistor. So that is what people think of as a tunneling transistor, and therefore you might be able to lower the supply voltage. All right, so that's how a transistor might look. This is a model. This is kind of how it works. So here's this band gap you heard in previous talks about in blue. And this gap is narrow in certain energy ranges of applied voltage. And eventually, you can have currents that are flowing through tunneling for a given set of biases. So basically, you can have a device that turns on and off rather steeply. And that's sort of the idea of a tunneling transistor. Now, you can have a tunneling transistor like this one, where it's single gated. You can have a tunneling transistor where it's double gated. You can have a tunneling transistor that's a nanowire. And you might want to compare these different geometries. And it turns out that really to beat 60 millivolt, a normal transistor configuration wouldn't even help you at all, even in this novel concept. It's actually very hard to get the right electrostatics, so you need almost a nanowire to do that. All right, so these are old slides. We've done this for a couple of years. Here are some newer slides where people try to achieve that with gallium nitride, and the details are that you have to have scattering in the device and model it well, so you can match experiments on even simple PN diodes. Then you can design transistors, and it turns out that the design of these transistors depends very strongly on, say, the indium concentration over here in this layer, or the thickness of the layer. And these effects are actually exponential. So you have to really design these things well to put them in a place where they can be operated well and have a chance to beat today's silicon technology. All right, here's another example that shows a complicated heterostructure where electrons actually flow up, so to speak, as they absorb phonons and thermal energies and kind of kill the performance that you would like to get. Rather than steep, it becomes less steep. So that's a key element of this transistor simulation. There's a lot of talk about alternative materials, dichalcogenides or black phosphor or indium arsenide. We can compare that in this whole frame set of modeling and compare different device technologies and capabilities. Now, Intel has designed a new way, or a way of comparing all these different design technologies. What is going to replace a CMOS transistor? And what they do is basically say we have a real full adder, and we have a delay. So basically speed, you want to run fast, right? And you want to consume very little power. So down here is where you want to be. And there's a whole world of people out there looking for the next replacement switch. And a lot of the technology that's out there on spins and magnetic devices is sort of up here. So they run really slow and cost a lot of energy. And these tunneling devices actually are sort of down here, and they're tending to at least beat the best silicon technology. So there's some hope in there, but it's really hard to do still. All right, so the tunneling transistor might come to the rescue for a little while on this aspect, but really what you need to look at is a chart of development where you look here again, an Intel chart, stuff that is actually in production and is being sold today. Let's look at the transistor a little bit. This transistor is so-called FinFET. It's basically, you can think of this as a classical hose with a grip around it. That's the electrostatic gates. Electrons flow through the blue surface. This is what a mechanical engineer would draw in a solid model. If you take an SEM picture of this, you see that this fin is 8 nanometers wide. And the gate is roughly 20 nanometers long. Now let me translate those numbers for you. 8 nanometers wide means 64 atoms. Okay, it's going to be kind of hard to make that smaller. And the length of 22 nanometers is 176 atoms. Now, if I take that back to, well, so if I take a cross-section, it's roughly only 1,000 atoms in the cross-section that is actively engaged. Now, if I take this development chart and say 22 nanometers, 176 atoms, and I'm going down to a 5 nanometer transistor, that thing is 40 atoms long. If I look at the critical dimensions of, say, a scaled fin, I'm going from 64 atoms down to tens. There is a physical limit of scaling, regardless of the commercial limit of is it financially viable to do that. And this is the agenda why we built NeMo, to do atomistic modeling of electrons that are out of equilibrium. Another aspect of all of this is the number of electrons that are governing the electron flow is going down to the tens. So you're really going towards single electronics rather than this cloud of electrons moving through the structure. So with this tool set, we can look at a lot of different devices, tunneling devices I talked about. We can do topological insulators. We did a lot of work on quantum computing for single atom transistors and electron flow, of what Irene Qualders talked about this morning. The overall agenda is really to bridge the gap from ab initio to devices that have a physical large extent that can actually be measured and in the laboratory. And what we really do is we bridge the dimensions and the theory aspect from going from diff diffusion, which is well established in electron flow, to Boltzmann transport. And when I went to grad school, which is a long time ago, it wasn't even clear what formalism to really use. And really the NEGF, non-equilibrium green function formalism, has emerged. And what physicists typically do, and what material science typically does still today, is they write down a Hamiltonian, they write it in DFT. They might have perturbations on this system to get really fancy, but fundamentally, it's really operated in equilibrium. Now, what you have here for an electrical engineer, you really shuttle electrons from one reservoir through a quantum mechanical system into another reservoir. That is fundamentally out of equilibrium, and that needs to be treated in the theory segment, and that is what this non-equilibrium green function formalism does. You can rederive it, the Boltzmann transport and diff diffusion, but it really gives you a unified model to look at all kinds of devices, very different devices. Silicon, graphene, carbon nanotubes, even molecular electronics. It's a matter of choice of Hamiltonian to put in and the interactions. So that's the fundamental piece. Then you have to have really multi-scale breakout of the structure from position of atoms to valence electrons and possibly electron-electron interactions. And I'm going to skip over the methodologies a little bit. There's a history of building this NeMo tool. So here's a picture of a resonant tunneling diode. That's the first NEGF tool that was being built at Texas Instruments, 94 to 98. And that code ultimately scales up to 23,000 cores. It's a 1D code, could deal with 1,000 atoms. Then at JPL, we built a code that can deal with 50 million atoms, but electronic structure. Then we parallelized it to the petascale. Then a follow-up code was being built. It can do 140,000 atoms in quantum transport in 3D. And the latest version, we can deal with 100 million atoms ballpark and have all kinds of physics, all crystal structures, and we're connecting it to DFT. So let me talk a little bit about science. Why do we need to deal with metal transport in metals? I've been traditionally a semiconductor person. If you look at power law, at the device that's down here, that's a tiny device. Then you have a huge tower of metal that sits on top of that. And in fact, most of the power that's now being consumed in these devices is not even consumed here in the little device, but it's actually in the metallic layers. So the metallic understanding on transport is really critical. So 50% of the power is really being consumed in the interconnect. So what's interesting here is that these interconnects are becoming small as well. You're starting to see effects due to grain boundaries and interface roughness on the metal itself, and you need to understand it, you need to model it. And unfortunately, the existing theories don't really work well because they're empirical and they have empirical fitting parameters. And what we can do with our code now is actually look at structures in an atomistic sense. We look at grain boundaries, we can look at interface roughness, and we can match to experimental data that is being taken right now at Purdue, where what we model is basically statistical samples that include grain boundaries and the sampling of them that give us error bars that can then match to experimental data quite interestingly. A lot of the computing we do is extremely compute intensive, and that's why we run on big machines. The system we use is localized orbitals. The Hamiltonian ultimately is sort of a banded thing, a block matrix type thing, banded through the middle of the structure. I'm going to skip through the details here, but basically you end up having to solve this system where each layer scales as n cubed, where n is the number of orbitals and atoms in a slice. And the memory footprint is large, and you might have to do this for large devices with lots of iterations, for lots of energy and k points, because you shoot electrons at different energies and at different k points. You have to do electrostatic simulations. So you do that quite a bit, and you can consume some 80 million CPU hours to just simulate a single device. That could be very expensive, and that's not really an engineering approach to running many different devices. So what we worked on is something called a basis set reduction, or mode space, where you take the full Hamiltonian and project basis states out to get a smaller Hamiltonian. And what we can do is basically speed up the code by a factor of 200 and reduce the memory footprint by roughly a factor of 10 with that methodology. And that allows us to touch realistically large devices that are maybe 5 nanometer in cross-section, which gets us close to this FinFET that I've been talking about. And instead of consuming some 547 million core hours, we can do much better. I talked about tunneling devices, so you have a disconnect between the traditional model of holes and electrons. How do you treat that in one? So we have a full electron model. There's work going on in recombination generation for solar devices. I'm going to skip over that. There's talk about quantum computing, so we worked on tunneling through single atom transistors. There's some recent work that was done on blue waters here. I'm going to skip over the non-local scattering. I'm going to skip over solar devices. So here this is an LED. And I'd like to finish up with giving you a pitch about nanoHUB, where people come and listen to over 5,000 lectures, some 500 tools that are being published on nanoHUB. These tools are now cited in Google Scholar and the Web of Science as a proper publication. And the NEMO software powers 9 tools that are inside apps of nanoHUB, which is a really cool thing now. 27,000 users can use that kind of tool without installing anything, running 500,000 simulations. And what I could have never imagined is over 3,700 students are now using these codes in classes. Formalized classes of project assignments, people that I could have never reached when I was still at JPL or TI. And nanoHUB affords me that possibility now. And of course, all of that is being done with a research group of students that do the real work. So with that, I'll